we're finishing up chapter 15. There are videos for everything that's covered in homework number 5 on our webpage, and that's been up for a few days. So hopefully you've gotten a start on that. If not, I did not put the due date for homework number 5 until Sunday because I got it to you guys so late. I am going to post a homework number 6. It's only going to have maybe 6 questions in it, just because I want to introduce you guys to chapter 16. And then I'm going to make a final exam review assignment so you have a good idea of what the final exam is going to look like and exactly what the questions are look like and how they're going to be worded. That is going to be in a homework format. That way you can use the Help Me Solve This button, use View an Example, and if you get it wrong, you can try it again, and you can do them over and over and over again. You are not required to do the review assignment, but if anybody does the review assignment, I will use it for 10% extra credit on your final exam. Okay? So if you're one of those people who sits there and tells yourself, man, I know how to do this stuff, but literally as soon as somebody says test, like, I can't. So you'll be able to see all the same types of questions, and you'll be able to work on them for over and over again for a long time so you get them correct. So that way, if you do mess up a little bit on the final, this can give you a little bit of a buffer. Okay? Anybody have any questions about that?
What day exactly is the final going to be?
The homework, so homework number 5 is already up for chapter 15, and that's due Sunday night. The homework number 6, which is only going to have about 6 questions, and the final exam review, which is optional. In the final exam, I'm going to post all of them today. My kids are going to their dad's house. I've got the entire house to myself. I'm so excited. So all of that stuff's going to get posted today, and it's going to be due by next Tuesday at midnight.
Okay.
Okay. So let me give you a scenario for that review assignment. I don't want you to think, well, I don't want to do it because I can only do a couple problems and I don't want to get a 20 on it and then have it mess up my grade. The whole entire thing is extra credit. So if you open it up for 20 minutes and are able to look at 3 or 4 problems and get them right and get like a 40, well, 10% of that is 4 bonus points. So I don't care if you get 100 on it. I would love for you to. But just know anything that you can do on that review assignment, anything at all, will help you.
I know it's just kind of good it worked out this way because I'm pretty much done with the other classes, my other 2 classes. So
okay.
I'm going to just focus on this class.
Okay.
Finishing it up.
Yeah, and I am without kids for 4 days. So I am doing advising and registration and just sitting here at my computer and getting stuff done. So I'm also more than happy to set up meetings with any of you guys individually. If any of you guys need some extra help before the final exam, I'd be happy to do that. I'm going to open up homework number 5. That way, if anybody has any questions specific to homework number 5, we'll have this here and we can go straight to it and see. Some of the questions I purposely picked because they were fairly simple and they didn't involve any computation, but it's important things to know. So like this first question just asks you which are the independent and which are the dependent variables. Do any of you guys have specific questions that you want me to go over for homework number 5?
I was working on it before we started, and I got up to number 8, and that's as far as I've gotten.
Okay. Did you get stuck at number 8, or that's just where you left off?
Well, I hadn't watched the notes yet.
Okay.
Did you put it up there?
Yeah, so this one's partial derivatives. That's actually a good thing for all of us to talk about together. So I think that's where I'm going to start. Partial derivatives, and then also the stuff that I just posted today. That way you can see it in real time and ask any questions instead of just completely relying on the recorded videos. Some of the videos are really, really good because some of these people have much more advanced computer software and they could do some really cool graphics and stuff, which I think is really helpful in Calculus 3 because so much of this is 3 dimensions and it's hard for us to draw that really accurately on paper by hand. So it's really nice to see a lot of these nice computer animations that really bring it to life nicely without having to try to interpret what my drawing looks like. So I'm just going to start with what exactly a partial derivative is, and then we're going to compute some. So in Calculus 1, one of the very first and most basic applications we learn for a derivative is an instantaneous rate of change. But in Calculus 1, we always had f of x equals y. It was only two-dimensional. There was one independent variable, and there was one dependent variable. So there was really no confusion about what we were measuring and with respect to who. So when we did this, to calculate y prime, we applied our derivative rules on the function, and we apply all of our derivative rules to the x's because x is the independent variable. Now that we're in Calc 3 and we're dealing with surfaces in three-dimensional space, we have got two independent variables. And there technically is not a derivative for a function of several variables. There is no one thing that we ever call the full and complete derivative when we're dealing with functions of several variables. That's because derivatives measure rate of change in one specific direction. So in Calc 3, when we have two independent variables, we can calculate our instantaneous rate of change with respect to either of those directions, but not both at the same time. So we would take our derivatives either with respect to x or with respect to y, but we wouldn't necessarily do both at the same time. So on this one, what we're looking at is a function z, which is f of xy. Since there are two independent variables, when we're asked for a derivative, we're only allowed to apply our derivative rules onto one of these variables at a time. And because we're only applying it to one variable, it's actually called a partial derivative. There isn't anything that is called the derivative of a function of several variables. All we have is partial derivatives, because we can only do this with respect to one variable at a time. So these partial derivatives are going to express instantaneous rate of change in either the x direction or the y direction, depending on which variable or which derivative we take. We can still consider these tangent slopes That's another application we used derivative for in Calculus 1. If we were ever asked to find the tangent, the equation for the tangent line to a function, we would use derivative to find the slope of that line. And that is that's still true here in Calculus 3. Those derivatives still represent slope, but we've got two independent axes here. So we have to specify which axis we're following when we're measuring that rate of change. So I'm going to try my absolute best to do a drawing. We'll see. Okay, so we've got our three-dimensional space. Let's say we've just got like this upside down elliptic paraboloid. So it looks kind of like a bowl, but it's upside down. If we were to take the partial derivative with respect to the x variable, that means as we move out along the x-axis, we want to know what is happening on the surface of our function. So if you follow this line here that I drew on the x-axis, and you draw the exact same line in the exact same direction along the function, you see that we've got this downward curving piece. So this derivative in the x direction is going to be negative because all of these tangent lines that point along the x-axis are pointing down. The way that we write a partial derivative looks like this really weird backwards 6 symbol. So this is going to mean the first partial derivative of z with respect to x. Because z is our dependent variable, that's what our function is equal to. And with respect to x means we're interested in what's happening in the x direction. And this also means that we are only going to apply our derivative rules to the x's that appear in that function. We don't care at all what is happening in the y direction if all we're looking at is what's happening this way. I'm going to change the color. We could also do this by moving in the y direction and asking ourselves, if I follow the y-axis as I move along my surface, what is my rate of change? Well, because I chose this elliptic paraboloid, they're looking the same, but they don't have to. These two can look very, very different. When you move in a different direction horizontally, it could make you move vertically differently. If you think about, I use this analogy all the time, and I don't know if it's a great analogy, but it makes sense to me. If you think about climbing a mountain, the XY axes are the latitude and the longitude, kind of, that you're located on the surface of the earth, and then the Z value is the altitude, how high you are on the mountain. So this could be a mountain here, and we could be located at a specific spot on that mountain, and we can try to determine, well, if I move in this direction, or this direction, or this direction, or this direction, what kind of slope am I going to be dealing with? Am I going to fall to my death? Am I going to need like climbing gear, or is it going to be just a nice, easy hike? And we can tell that with these partial derivatives. Questions so far? So this is just kind of a background of what are they. So just for completeness, we could also do the partial derivative of z with respect to y. That means we're asking what the slope is if we choose to follow the y-axis direction. And to calculate this, because it's with respect to y, that means we only apply our derivative rules to the y's in our function. The derivative rules that I'm talking about are the exact same derivative rules that we learned in Calculus 1. We need to practice these, though, because there is going to be something slightly different about them. We're going to see more than one variable, more than one independent variable here, and whatever variable you are not taking the derivative with respect to, you just leave it alone and you treat it as either a constant or a coefficient, depending on where it's located. So when we're taking partial derivatives, any independent variable besides the one that you're taking the derivative of, sorry, it takes so long for me to write. What I find is that people don't have any trouble usually remembering their Calc 1 derivative rules. Usually the trouble is training your mind to ignore variables in Calculus 3 now. So when taking partial derivatives, any independent variable besides the one that you're taking the derivative with respect to will be left alone and treated as either a constant or a coefficient. We treat it as a constant if this additional variable is contained within its own term. And we consider it a coefficient if it's being multiplied by other variables.
We're in class right now. I was going to tell you guys.
Well, we can hear you. It sounded like Will. I don't have my videos up. All right, so we're going to look at a couple of examples. And all we're being asked to do here is find both first partial derivatives. And for our first one, we are dealing with the function f of xy equals 3x squared y minus 2y sine x. We want to find both first partial derivatives. Has anybody already watched the videos or tried some of these and know what they mean by finding both of them?
When you take the derivative of x and y.
Right. We've got two independent variables here. That means we're going to have two partial derivatives, two possible partial derivatives. So they're saying find both of them. If this was like f of xyz, then there would be three different first partial derivatives because you could do the derivatives with respect to x or y or z. Yep. So it just means do each of them. Okay. So the first one is the partial derivative of f, because that's the name of our function, with respect to x. And there's some other notations that you might see besides this one. We could also call this f subscript x. That one is used very commonly to represent partial derivatives in a specific direction. What we do not use here in Calculus 3 are those little apostrophe symbols that we used to use for derivatives in Calculus 1. We do not use those here. Because every time we take a derivative for functions of several variables, we have to indicate, oops, I'm still on my eraser. We have to indicate with respect to which variable it was. So just throwing a little prime symbol on it's not much help here in Calc 3. So we go ahead and just write the variable as a subscript to let everybody know which derivative we took. So f sub x, or partial of f with respect to x, means we need to look at this function. We need to find all of the x's. Oops. There's one there. There's one there inside of the sign. Okay? So those are the two things that I have with x's. How would you take the derivative of an x squared?
Two x?
It's just 2x, right? That's a power rule. So exact same Calc 1 rules. The derivative for x squared is 2x, but coefficients get transferred. And in this case, because the y is being multiplied, or up here I said if the y is together with other variables, then it's considered a coefficient, and you're just going to scoot it along to the next step. The only derivative that was taken was for the x. And then we also have to do this for our second term. We need to know the derivative for sine x.
Cosine x?
Cosine x, yep. What do you think we're going to do with these guys, the 2 and the y?
They just drop down.
They just drop down and stay, right? Those are considered coefficients. So if we just clean this up a little bit, we're going to have 6xy minus 2y cosine x. That is our first partial derivative with respect to x. We could also calculate the partial of f with respect to y. And even though these two derivatives, I said x, even though these two derivatives are coming from the same function, there's no guarantee that these two partial derivatives are going to look anything alike. They could be very, very different. But this time we want to reference that original function again, but this time we want to go through and take the derivatives for the y's in the equation. So I'm going to go back and I'm going to find all of my y's. And I'm going to do my derivatives for just the y's. So here in my first term, it's just a y to the first. So what do you think the derivative for 3x squared y to the first is with respect to y? What normally happens to a linear y when you take the derivative?
Becomes 1.
Right, it just turns into a 1. And we can show that with power rule as well, because old one comes out front, new one is 1 less. So you end up with 1y to the 0, which is just equal to 1. And then the 3x squared is a coefficient, so the 3x squared is just going to get passed along to the answer. All we did was took the derivative for the y. And then what do you think that second term is going to look like if we take the derivative for just the y?
It should be 2 cosine x, right?
Nope, you're close though. We're definitely going to pull the 2 out. Pull the 2 down because it's a coefficient. The y is linear, so you were right to not have a y in there. But because this piece right here only has x's, you don't do anything to it except transfer it down. Yep. So we don't have to say times 1. We could just say 3x squared minus 2 sine x. But that's a very common mistake, and that's why I wanted to show these live to some of you guys, because it's hard to see that and not want to change it to cosine. But if we're doing this with respect to y, the y is not inside of the trig, so the trig's not going to change. It's all multiplied, so it's just considered a coefficient. All right, we're going to try one more really quick. F of xyz is equal to xy to the 4th minus natural log of xz squared. I had to throw that natural log in there. I think there might be one in the homework. That's why. Because there are 3 independent variables, this function actually has 3 partial derivatives. So we're going to be calculating the partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z. And each one of those just means only consider that particular variable to be the true variable, and the other guys are just constants and coefficients. So anybody who feels comfortable turning their microphones on, remember, it's perfectly fine to not be correct. I'm going to see if you guys can help me with the answers for these. So remember what I do. If I want partial with respect to x, I need to go in and find my x's. The x in the first term is linear, and we just saw that in the last function with the y's. So with respect to x, what do you guys think this first term will have a derivative of? We're just taking the derivative of the x here, which is x to the first.
The x will go away, and it should be 4y cubed.
Nope, don't do the derivative for the y.
Oh, okay.
Only the x. And anything else just gets transferred down to the answer. So when we do the derivative for x to the first, it's just going to turn into a 1. And then the y to the 4th, because it's not an x, it just gets transferred to the answer. So we've got 1 times y to the 4th. There's also an x in our second term, and that x is inside of a natural log. So we have to remember how to take the derivative for a natural log. So just as a little side note over here, anytime you want to take the derivative for a log with a bunch of stuff inside, you're going to take all the inside stuff and put it in the bottom for a fraction, and then you're going to take its derivative and put it in the top of the fraction. So this is how we take the derivative for anything that's inside of a log. So the first thing I'm going to do is take everything inside and put it in the bottom of the fraction. And then in the top, I want to put the derivative. And in this case, we're only taking the derivative with respect to x. So if I take the derivative with respect to x of just that stuff inside the natural log, what should I put in the top for the derivative?
1.
A 1. Yep, the derivative of x to the first is 1. And what do we do with that z squared?
Don't change it, right?
Do not change it. Yep, because we're not doing derivatives of z's. We're doing derivatives of x's. That means it can just get transferred down to the answer. So we've got y to the 4th minus, ooh, those guys cancel. Y to the 4th minus 1 over x.
Oh, so you do have to add it in the numerator?
Yes. Yeah, you always have to have a numerator in that fraction, and the numerator is the derivative of the inside stuff. Yeah, so even though the z squared cancels, this is really just division. So if you divide something by itself, the answer is always 1. And in the bottom, we still had the x. All right, I'm going to turn off my microphone for a minute, and I would like you guys to try to find the partial with respect to y and the partial with respect to z. All right, if anybody would like to share or is confident in their partial of f with respect to y answer, I would love for you to share it with all of us.
I don't know if it's right.
That's okay.
I'm looking at it. Is it 4y cubed to x? I don't know. I messed up.
We're going to do the power rule on the y to the 4th, which is 4y cubed. Yep. And then the x is going to transfer down with it. It doesn't matter the order that you have those written in. Yes.
Okay.
Is that your final answer?
And then for the other part, it just cancels out, right?
That is right.
Because you can't change anything to it. So yeah.
There are no y's in that second term, which means that second term, with respect to y, it's a constant. If we're considering only the y's to be variables right now, then that second term is a constant, and the derivative for a constant is 0. So yeah, our answer here, I just like it in alphabetical order. I would say 4xy cubed. That's it. Anybody get something different or don't understand quite how we did that and want to ask before we move on? Okay, we need somebody else to do our partial derivative with respect to z. That means we're only going... Oh, who we got?
I got negative 2 over z.
Negative 2 over z. All right, so let's see how we get this. What did you do about the first term, Baden?
Right?
Right, it's a constant because there are no z's in there. So that entire first term is a constant. Its derivative is 0. Yep. So we've got 0, and then we've got minus, and then our z squared is inside of the log, so we do this rule again, which is put everything from the inside the log in the bottom of a fraction, and then take its derivative and put it in the top of the fraction. And remember, we're only doing the derivative with respect to z. So power rule on z would give me 2z, and the x would tag along, right? And those x's would cancel, and one of the z's would cancel. So you're exactly right. We just have negative 2 over z. So that one's a little bit tricky because of the logs. Logs are just probably not something that you see regularly. You may not remember this derivative formula here. Excellent. Those are partial derivatives. We're going to take a 10-minute break at 3, but in the next 15 minutes, I'm going to do section 4 as well. Because there's only one thing that I usually cover in section 4, and it has to do with partial derivatives again. So it's perfect to just go ahead and do all of it here together. 15.4 actually, I think the name of that section is the chain rule. But the one concept in that section that I find most useful and most interesting is how we can take implicit derivatives we can find implicit derivatives using partial derivatives. If we have some function z equals f of xy, in order for this to work, we have to get everything on the same side of the equation so that one side has nothing left and it will be equal to 0. So let's say we're going to subtract the z over from the left-hand side to the right-hand side. We're going to be left with 0 equals f of xy minus z. This guy right here, for surfaces in space, is a lot more useful because it is one expression that includes all of our variables. So this guy has his own special name. He is capital F. We like to use the same letter because they're related, but we switch from a lowercase to an uppercase just to kind of drive home the idea that they are not exactly the same. This is f of xy minus z, which is also equal to 0. So this is our capital F. Back in Calculus 1, I say that a lot, you could have been asked, and I think this is in the section having to do with applications of derivatives, you may have been asked at one time to find dy dx for 5xy squared minus x cubed y equals 12. So this is only a function of two variables. So this is a perfectly legal Calculus 1 problem. The problem is it is given to us implicitly. And what makes this implicit is that it is not solved for the dependent variable. If there's only two variables there, x and y, then we know it's always assumed that y is some function of x. Here's our dependent variable. Here's our independent variable. And usually they're separated on either sides of the equation. But this one, they're kind of all jumbled together. So that's what makes it implicit. I'm not going to go through the entire Calculus 1 method, but I'm going to start it because I think I need to remind you of this horror so you have much more motivation to learn how to do this with partial derivatives. So, in Calc 1, if we were asked to do that derivative, dy dx, we would go through this entire equation and take the derivative of everything with respect to x. And then we need to continue assuming that y is a function of x. So anytime I take the derivative of a y, we've got to use the chain rule and include a dy dx. I'm only going to do the first term. Once you see the first term, you might remember. This is a product, so we would have to do product rule on it. So I've got the derivative of the first times the original of the second plus the first times the derivative of the second. I have to do power rule, and then chain rule tells us we also have to do dy dx. Because y is a function of x, we just don't have it solved for x right now, so I can't tell you exactly what it is equal to. And we would continue this And then we would combine all the dy dx's and factor and divide, and it was a really long, tedious process that ended up having lots of product rules. Now that we know partial derivatives, we could take this function, let's say, do we have an actual function there? We do. I'm going to use that same one. (5xy squared) minus x cubed y. Stop. We can find that exact same derivative using partial derivatives. The first step is to create your capital F function. And the capital F function means that everything in that equation is on the same side of the equation. So we're going to have to subtract that 12 over to move it, because we need everything together. So that would make this f of xy equals 5xy squared minus x cubed y minus 12, which is equal to 0. Capital F function is always equal to 0. We can find the derivative of y with respect to x by calculating the negative partial of our capital F function with respect to x divided by our partial of the capital F function with respect to y. So we negate and we flip. Notice x was on the bottom here and it went to the top, y was on the top here and it went to the bottom. So you always negate it and flip it. So we want to go through and find the partial derivative with respect to y and x, which is going to be much, much easier than the Calc 1 way, because when we do partial derivatives, we don't think of this as a product rule. We say, okay, only treat one as a variable and treat the other as a coefficient. So that's one of the reasons this is so much easier. So the partial with respect to x is going to be 5y squared minus 3x squared y, and then the 12 zeros out for derivatives. The partial with respect to y is 10xy, because the 2 comes out, minus x cubed. And then again, the 12 zeros out because it's constant. And then we've got a negative out in front of this whole entire thing. Like, we literally just did a 30-minute Calculus 1 problem in two minutes. We would get this exact same answer in Calculus 1, but it literally would take up an entire sheet of paper in 30 minutes of your time. So I love it when we learn a bunch of new stuff that is a whole lot easier and gets to replace some of the old crazy stuff. I'm going to give you one more example for this, using these partial derivatives to calculate implicit derivatives, and then we'll take a break. Sorry. That was the other. That's a different one I had. All right, we've got this three-dimensional equation. Three-dimensional equations always create surfaces in space. 2x cubed y minus 5yz squared equals xyz. No clue what that thing looks like, but it's going to be some sort of surface in space. So it's completely legitimate for us to want to know what the change in z with respect to x is. Since this is a surface in space, we could figure out how quickly we're rising or falling if we decide to walk along the x-axis. And we can do this with our partial derivatives, since this is implicit, by calculating negative, and remember those guys are going to flip, f sub x over f sub z. So negate and flip. This right here is not big F. Big F has everything on the same side. So that xyz is going to have to get subtracted over. So our f of xyz function, capital F of xyz, is going to be 2x cubed y minus 5yz squared minus xyz equals 0. We want the partial derivative with respect to x on the top. So we go through the whole thing and do your derivatives with respect to x. So that would give me 6x squared y. There are no x's in the second term, so the derivative is 0. And in that last term, the x is linear, so we're just left with the other guys. And we're done with that. F sub z. Now go through and do the derivatives for just the z's. There's no z's in the first term, so the derivative is 0. In the second term, be careful because that negative still applies to it. So if we pull that 2 out front, we got negative 10yz. And then here z's linear, so it's going to be minus xy. And then we want to, remember, negate that whole thing. When you negate the whole thing, you can either leave it out in the front, or you can distribute it in the top, or you can distribute it in the bottom. But don't do all three. You choose one of them. So we're either going to leave out front, distribute through top, distribute through the numerator, distribute through the denominator. You only choose one of these. You don't do all of them. And
Why is that?
It is because, I'll show you with some regular numbers. Oops, let me finish these notes real quick. Okay, so as a quick example to show you why this is, if I had the negative of 3/5, we could get that by either leaving it out front, oops, or by calculating negative 3 divided by 5, or calculating 3 by negative 5. But if you tried to give it to both of them,
Yeah, make it positive.
right, they're going to cancel each other out and change it to positive. So we only want it in one place. We only want it applied to one thing. Otherwise, we introduce extras and then they start canceling. So out front, in the top, or in the bottom. You choose one.
I mean, technically, you could do all three at once.
Oh, yeah. You could do all three, because 3 negatives will result still in a negative. Yep. Zachary, I don't mean to beat this to death, but another way you can think of this is anytime you see a negative, it's equivalent to multiplying by -1. So this is the same thing as -1 times 3/5. And if we change that to a fraction, because when we multiply fractions, we multiply the tops together and the bottoms together. you get negative 3 over 5. But this would still be negative 1 if it was 1 over negative 1, and the negative went to the bottom. And it's still all equal to the original, which had the negative out front. So front, top, or bottom, those are our choices.
Okay.
I am recording this, finally. I keep saying I'm going to record it, and then I always forget. But I am recording this, and I am going to save these notes, and as soon as we hang up at 4, I'm going to post all this on Moodle. Allison was not able to be here today, so I promised her I would do that, so she didn't miss it. Anybody have questions so far? Partial derivatives?
So when they don't have the z, like you were saying before, the constants just cancels out, or what?
Yeah, if the entire term does not contain the variable that you're working with. So 2x.
That was the only thing I didn't get.
Okay, so this has 3 different terms. Terms are separated by pluses and minuses. So this is a term. And this is a term, and this is a term. And all of their derivatives can get done individually. And we just leave the same signs in between. They might change later, but just keep the same sign in between. And we can treat each of these as their own derivative. So if we were doing the partial with respect to y, that first term does have a y, so we'll go ahead and do the power rule. Well, 3 times 2 is 6. So I'm going to say 6xy squared. The second term also has a y, and it's a y to the first. So the derivative of that is just the 5z. This last term has no y's in it. That means its derivative is 0. No y's means constant.
Yeah, that's all I wanted to know.
Yep.
Just wanted...
If we changed this to calculate the partial with respect to x, which term would be constant?
Say that again.
If we wanted to calculate the derivative with respect to x,
it would be the middle term.
The middle term is a constant with respect to x, and its entire derivative would be 0 in the middle. Yep. Yep, so you just got to be really careful and keep in mind which variable you're doing your derivative with respect to. That's the only letter that you should apply your derivative rules to, and everything else either just gets carried along for the ride or it gets zeroed out. All right, so section 5 and 6 of chapter 15 have just a couple of more calculations to learn for three-dimensional space and functions of several variables. In section 5, we're going to learn about the gradient and directional derivatives. And then section 6 is a mixture of 2 concepts. It's gradient and planes, like when we set up the equation for a plane. So it's just going to be a combination of those 2 things put together. And we'll know how to do both of them individually, so really just have to explain how we're going to use them together, and I'll show you an example. So in the last section I told you that there really was no one thing that we call the derivative of a function of several variables. But if there was anything that we wanted to call our derivative, it would be the gradient. So if we've got a function of 2 variables, x and y, the gradient for function z. It's an upside down triangle, and it's also called del. It's called the del operator. If anybody's going to go on and take a lot more math or physics or anything kind of math, science, engineering, theoretical, you might see that del symbol again. Anytime you see the del, keep this in mind, anytime you see the del, you're going to be dealing with a partial derivative. Remember the Greek letter delta we use in algebra and calculus to represent like change, one-dimensional derivatives. So that upside down one is partial derivatives. We also could write this as the gradient of f. And I hate this one, but I have seen it before. They just say grad f. I don't like that one. I like using the weird symbols. So, upside down triangle. And the way exactly we calculate this is with our partial derivatives. The gradient is a vector. So it's going to have an I component and a J component. And that's not a J. So gradient is a vector. Which means I know it's going to be in this format. For the I component, we put our partial derivative with respect to x. For the J component, we do the partial derivative with respect to y. So this is why they say if anything can be considered the actual derivative for the function, it's the gradient, because it involves all of the first partial derivatives. So you just take your first partial derivatives and write them as vectors, vector components for ij and possibly k. What the gradient tells us is if we are standing on a surface at a particular point, the gradient individually, those two numbers tell us what the slope in the x direction is and what the slope in the y direction is. But on a smooth continuous surface, you should be able to find all of the slopes all the way around the surface at any spot if you know your x and y partial derivatives. Because if this is a smooth continuous function, every single point should be connected, which means every single slope is represented and it is continuous. So let's say I'm standing right here. So I came out some on the x-axis, and then I went up some. The gradient at that spot is going to tell us two things. It says, well, from this spot, if you decide to follow the x-axis, this is going to be the value of your tangent slope. If you decide to follow the y-axis, no, why do I keep doing that? If you decide to follow the y-axis, which is this way, then when you, this is going to look so weird, but when you follow this surface in the y direction, you're actually staying level. We're going down if we go in the x direction, but we're staying level if we go in the y direction. So two completely different slopes in two different directions, and every single slope around this point, no matter which direction you want to go, is just a combination of those two slopes. We can't create some random slope of 5,000 if neither of these ones are that extreme. So if this is a smooth, continuous curve surface function, then all of these slopes will gradually change, which means they can be combined to create all of the slopes. And all of those slopes in all those different directions besides the x and y direction are called directional derivatives. So if we want to calculate the slope in any direction other than the x or y directions, it is called a directional derivative. And it's going to be a combination of those two. And since these two, derivative with respect to x, derivative with respect to y, are stored in the gradients, the gradient and the directional derivative are very closely connected. And I'm not going to do an example for gradient yet until I finish directional derivatives. If we're asked to find a directional derivative, there are two pieces of information that we need to be given. We need to know what surface we're standing on, so they need to give us some sort of three-dimensional function. And then we have to know a location, so I guess there's three things. We have to know where we are on that surface, and then we also need to know what direction we're interested in traveling. And the direction here is based on x and y axis. Sometimes you can like use north, south, east, west stuff. But if we give it an xy direction, it will tell us what the slope is in terms of z in that direction. So we need a surface, which is our function. We need our location, which is ordered pair, x, y. And they might also give you z, even though you'll see that we don't need it if they do. So sometimes z, but don't worry about that. The third thing we need is a direction. And there are three different ways that you could be given direction. You can be given direction as an angle. This is the standard position angle where we're measuring counterclockwise from the positive x-axis. What else has direction? What have we been learning about all semester, and we say one of its components is direction?
Magnitude.
Magnitude and direction go together to tell us what? I think two people just talked at the same time and I heard magnitude. If we have
Vector.
it's a vector, right? We know vectors have direction as well. So they could give us a vector to represent the direction they want us to travel in. Hopefully, though, this may be a unit vector. If it's not, we have to change it to a unit vector. And they could also just give us 2 points. They could say you're traveling from this point to this point, and in that case we could calculate the vector on our own. So let me just do those two. Those are the two main ones. So we need to set up a unit vector to represent our direction. If they give you direction as an angle, all you have to do is do cosine theta I plus sine theta j. If they say go in the direction 45 degrees, then the way that we write that as a vector is we're going cosine 45 in the x direction, and we're going sine 45 in the y direction. This is a unit vector already. So if they give us an angle, there's nothing we need to do except the sine and cosine. If they give us a vector, we need to make sure that it's a unit vector. So if they're giving us a v, we need to calculate the equivalent unit vector, which would be v over magnitude v. So the moral of the story here is you have to have a unit vector as part of your calculation for our directional derivative. So we need a surface, a location, and a direction. With the surface, come on, pages. Let's add a couple more. Since our goal here is a directional derivative, if they give us some surface f of xy, we know that the derivative in any direction is always going to be a combination of the partial with respect to x and a partial with respect to y. So we need to calculate the gradient, because our gradient is a vector that contains those two components. So we want to calculate our gradient. And then our directional derivative for f at location xy can be found by doing a dot product between your gradient and that unit vector we said we had to have, either from an angle or from a vector. All you do is dot product. So this one's going to have an x and y component, this will have an x and y component, and we'll end up doing x1, x2 plus y1, y2. Is that answer a vector?
No.
It is not a vector, no. When we do a dot product, we get a constant, which makes sense because we're finding a directional derivative. And back from Calculus 1, one of the basic applications for directional derivatives, or for derivatives in general, is slope, finding a tangent slope. So it makes sense that this is not a vector. This is representing a slope. So this is giving us the slope on the surface f of xy at some particular point in the direction of our unit vector. So we need our surface, we need a location, and then we need a direction that we want to travel. And if we know all that, then we can figure out what the tangent slope is. And all it
I
is...
had a question.
Go ahead.
I had a question about one of these from the homework.
Sure.
I could do the first part of the question,
Mm-hmm.
but then when it came to the directional derivative, it was like giving me weird answers that I was not getting.
Okay. Let me see. Those are at the end.
Number 50.
Okay. Oh yeah, and this is why I threw the log into the lecture today, because I knew I had one with a log in the homework. Okay. Have you checked yet to see if the issue is they want like an exact answer and you're given a decimal?
So for one of them I did, my answer that I got for the directional derivative was -4/11, and the answer they got was -4/11 square root 5.
Ooh, okay.
And I don't know where the square root is coming from.
Okay. Let me please. I don't know if I know how to do that. Yeah, there we go. Sorry, it's so small. I'm just trying to get it all on the screen. So we're given the surface, and everybody's number 15 looks like this. It's not exactly the same, but it's very, very similar. So we're given the surface natural log of 5 plus 2x squared plus 2y squared. We're given a location of 1, -2. And we are given a direction vector of 2, 1. The first thing they ask for is the gradient. So for gradient, we're just going to do partial derivatives. And everything is inside the natural log here. So remember, we're going to make a fraction. Everything goes in the bottom, and just the derivative portion goes in the top. So the derivative with respect to x is 4x. And then the derivative with respect to y is 4y. And that does not simplify. We cannot simplify those right there because of that plus sign. So that's it. That's the answer for the gradient. And then we're going to do... I think I know how they got the root 5. We are going to plug our point in because we want gradient at that specific spot, and we want it in this specific direction. But the direction we use always has to be a unit vector. We don't care how long this vector is. It's not going to change the direction of the vector, and all we want is the direction. And I know it's been a long time ago, but back in chapter 13 it was, I think, when we first learned unit vectors, I remember saying that anytime we use a vector for just its direction, we have to change it to a unit vector. So right now, v is 2, 1, and that is not a unit vector. So we calculate the magnitude of v, which is radical 5. So the unit vector is going to be 2 over radical 5, 1 over radical 5. And we're going to plug that actual point in to our gradient. They said find this at 1, -2. So after you find your gradient, you can go ahead and plug in the points x equals 1, y equals -2. And we get 4, 5, and 2, and 8. So 15. And then 4 times -2 is -8. instead of saying plus a negative, it's just personal preference. I'd rather say minus. And it's the exact same denominator, so minus 8/15 j. That is the gradient at that particular spot. So to get our directional derivative at 1, -2, we need to do the gradient at 1, -2 dotted with the unit vector we created. And for dot product, remember, multiply x components. So I'm going to have 2 over radical 5 times 4/15, and then multiply your y components, 1 over radical 5, -8/15. And then we'll simplify as much as we can. What in the world? I got 0. And that's possible because this is not Baden's specific question. This is just what came up when I said preview the homework. These are exact same things.
Yeah, I went back and did it, and with the unit vector, that was what the problem was. I forgot about that.
As soon as you said, like, as soon as I heard the difference was the radical, I figured that's might be what it was. So you guys have a problem just like this. Remember, to do the derivatives of those logs, you just create a fraction, you put all of the insides into the bottom, and you do the derivative in the top. And these are partial derivatives. So for that first one, we only want the partial with respect to x. So we're just doing power rule in the 2x squared. And I will, again, post this on Moodle if anybody wants to look back to it.
I have a question.
Go for it.
Okay, so when you got 15 at the denominator, did you plug in 1 for the x's and -2 for the y's?
Yes.
Oh, okay.
Yep.
Because I was working on the same problem yesterday, and I was really confused on how they got the answer as well.
Yep, so 5.
And I just didn't know which way to go.
And then 1 squared and -2 squared. Yep. So make sure you do your powers first. So this is the same as 4. This is the same as 1. And then do your multiplication. That's 8 and 2 and 5. Yep, so 15. So just be really careful when you do it because there's so many different operations going on there.
Okay.
But yep, once you get your gradient in this format, then all you have to do is plug in the point that they gave you for the x's and the y's. More questions? All right, I want to show you tangent plane really quick. It also uses gradient, so it's still part of the same conversation. But we found that this guy had a tangent slope of 0, which means we're standing either at a maximum or a minimum. We're at a spot where it's completely flat. You remember that from Calc 1? A 0 slope means horizontal. All right. Nope, not example. I'm going to talk about 15.6 for a minute. Section 15.6 is tangent planes and linear approximations. But we are not going to look at the linear approximations. We do a ton of linear approximations in differential equations. So if anybody needs that, you will get it in Math 285. So this is still along the same lines of working with a function of 3 variables. So we've got some sort of surface in space. And I'm just going to use, I think one of the videos I posted for this gave a good picture. That's why I picked that one. So we've got like an upside down elliptic paraboloid, and we're at one specific spot on this surface, so we can call that point P. And we want to know what the tangent plane right there looks like, which means I want to create a plane that touches the surface at exactly one point, which is that point right there. In order to do that, the plane and the surface have to have the same slope at that exact same spot. We don't really have anything called slope for functions of several variables. What we have, and the closest thing we have to it, is gradient. So for surfaces in space, if we want to find a tangent plane, and this also was a long time ago, for any plane, the two things we need are a normal vector and a point. Those were the two things that we needed in order to write the equation for a plane. So they have to give us a point in order to do this calculation. And for the normal vector, we're going to use the gradients. And we don't have enough time left for me to prove this for you or show exactly why. But if we've got z equals f of xy, remember that capital F function, if we put everything on the same side of the equation, so we'd have like f of xy minus z, and that's always equal to 0, we could do the gradient for the capital F function at that particular point and use that as the normal vector. So the gradient of our big F function, that vector is always normal to the surface. It will be pointing straight out at a 90-degree angle. So that's exactly what we need in order to write that tangent plane. So we're going to find the general form of the tangent plane to the surface x, y, z equals 10 at the point 1, 2, 5. So we've got a surface and we've got a location, but what we're being asked to find here is the equation for a plane. So it definitely would be useful for you to remember back when we learned just in general about planes. In order to be able to set up the equation for a plane, we need a normal vector and we need a point. So the new thing that we've learned is that the gradient for our capital F function can serve as our normal vector. So the capital F function is when all of that stuff is on the same side, set equal to 0. So I'm just going to subtract the 10 over. Our capital F here is x, y, z minus 10. Our normal vector is going to be the gradient for the capital F vector. And it has 3 variables. So this is now going to be a vector with 3 components. and we're going to have 3 partial derivatives to do. The partial derivative with respect to x for this function is just yz. The partial derivative with respect to y is just xz. And this is because the only place we have them is all together multiplied there. And then the partial with respect to z is xy. This is a formula for the normal vector anywhere on the surface. We just want to know what it is specifically at the point 1, 2, 5. So we can plug in x equals 1, y equals 2, z equals 5. We'll get 10i plus 5j plus 2k. So our normal vector is 10, 5, 2, and our point is 1, 2, 5. And now at this point, we just have to remember how to set up the equation for a plane. Remember, these guys are our coefficients, and those are our constants. So we do 10 times x minus 1, 5 times y minus 2, 2 times z minus 5 equals 0. And since they asked for general form, we'll go ahead and distribute. So 10x minus 10 plus 5y minus 10 plus 2z minus 10 equals 0. And then you can combine all those constants and either keep it on the left as a minus 30, or you can move it over to the right as an equals positive 30. Okay, so really just one new thing there in that last section is use the gradient of the capital F function as your normal vector, and then proceed as usual.